The MRS Symposium X lecture series invites some of the biggest names in materials research to present their work to their peers, and we are honored to have one of this year's lecturers, Silvia Vignolini, here with us to discuss her work today. Pleasure to speak with you.
The pleasure is mine.
Absolutely. All right, let's get started. So what exactly is structural coloration?
So you see, the color that you have around you usually are made out of pigment, and pigment are chemicals, molecules that are then embedded inside materials. And so, but pigment, the color that you perceive, it's a chemical characteristic of the material itself. In contrast, when you look at structural color, also the word says they don't depend on the chemical composition of the material, but depends only on the structure. And this sounds a little bit a difficult concept, but in reality, we have the example in front of us every day when you look at a soap bubble. Mm-hmm. The color of the water and soap is transparent, but as soon as you make the bubble, you are creating a structure that is capable to interact with light, with a phenomenon that is called interference, and then you can get coloration out of any material. And that's the principle that for which you have structural color.
And this is something that is naturally occurring in, say, like peacocks.
Yes.
How do you recreate that in man-made materials?
So you find the structural color in many different organisms, and many different organisms use different materials because not every organism has the right building blocks. We have been inspired a lot by the structural color that are produced by plants. And in the case of plants use cellulose to make a really strong blue coloration in many leaves or fruits. And we have been mimicking, using the same material as plants, so cellulose, the same architecture that we find in nature, by a concept that is called self-assembly.
And so what does this biomimetic process tell us about the natural occurrence?
So understanding how we can process cellulose at the nanoscale, we can also have insights on how these processes are working in the plant cell wall. And even if the principle of creating this structural color out of cellulose in the plants and in the lab are very, very different, there are some physical chemistry principles that can be still applied. And I think it's really interesting to discover them in the plants and apply them and then in the lab, and vice versa. While doing the things in the lab, you have insight of actually how nature creates them, because it's not really easy to look at development of this type of system in living natural processes in plants.
So can you tell us a little bit more about the applications for photonic materials?
Yes, so photonics materials mainly used in the context of optical fibers or optical circuits, but there is a much more, if you want, common application that could be really the production of pigment. In fact, the way that pigment are produced today in industry, it's really unsustainable. You have a lot of chemicals, polluting chemicals, a lot of use of energy and water. Mm-hmm. And therefore, if you could actually engineer this photonic pigments starting from natural material and using self-assembly processes, in principle you could really obtain pigment and color that are much more sustainable. And I think this is very important, especially in this context where textile industry is becoming one of the main contribution to CO2 emission,
right.
To find ways to also make color in a more sustainable way.
Right, a more environmentally friendly way.
Yes.
Well, your research is absolutely incredible. Thank you so much for your time today,
Thank
and congratulations on your recognition this year.
Thank you.